Uh, I'd like to thank the organizers, especially Professor Chun Jong-il, for the invitation. I began to think about multivariate public key crypto system only recently at the urge of my colleague and dear friend, Professor Chun Jong-il. He really urged me to look at this, and so he felt that algebraic geometers can contribute a lot to this community. So I began to think about it, and I realized that there are really lots of things that, and many interesting questions that for algebraic geometers. And I do believe and hope that by working together, you can, by using this platform and new point of view, you can improve the existing systems and also come up with new ideas. And that's really all I want to say. I can essentially finish my talk here. But let me move on. So this is, already I said this. The goal is to revisit the existing systems from geometers' point of view and reveal some new structures. So I will mainly focus on the analysis of MI system and Elliott tax. And also I will talk about classification problem. So it's given a quadratic form f, one can construct, not a form, but it's a series of forms. And one can construct other equivalent MPKCs by composing with invertible affine maps. And the problem is to classify all equivalent classes and determine which are good ones for practical purpose. And if you're an algebraic geometer, then this is really the problem that we like. And I will discuss the efficiency of direct attacks via Grosvenor basis. And here, what's called Castelnau-Beaumont for regularity and degree complexity play an important role. So I will talk about that. So typical MPKC consists of a finite field K and polynomial maps from Kn to Kn. The public key consists of the field K and the composition of the polynomial maps. So F bar is the composition of these L polynomial maps. And the private is key consists of these individual factors. And you want to keep the degree of the polynomials low for efficiency reasons. And also, as was discussed in Professor Takagi's talk, even if you use only quadratic equations, the ideal membership problem is already NP hard. So you do not lose too much by keeping the degree low. So I will describe Matsumoto Imai system for those who are not familiar with it shortly. The Matsumoto Imai system and many others use just one quadratic nonlinear factors. So among these F1 through FL, just a single Fi is nonlinear, others are linear or affine. And what's called the triangular schemes. I'm not going to talk about triangular schemes in this talk, but there are other MPKCs which use multiple nonlinear factors. But they utilize certain methods so that the end result, the public key, consists of only quadratic equations. And just like RSA is built upon the fact or the premise that the factorization in Z is hard, this MPKC is built upon the premise that factorization in the automorphism group is hard. So you are given F bar, but it is really quite difficult to factor F bar into these L factors. So composition is the multiplication in this automorphism group. So it depends on the complexity of the group structure of the automorphism group. So I'm going to assume that not everyone here is an expert in MPKC, and I'm going to spend 2 slides explaining the Matsumoto Imai system and Ellie attack. So I'm given a finite field. Q is the cardinality, and although it's not necessary, I'm going to assume that the characteristic is 2. So you pick an irreducible polynomial of degree n, and k, capital K is k bracket x mod g, so it's isomorphic to kn. So I'm naming phi as the isomorphism sending ai xi summation to ai, the coefficient vector. And you choose theta wisely, then this map phi of x to the, you're sending x to the q to theta plus 1. If you choose theta wisely, then this becomes invertible. So you have an invertible map from k to k. And now by composing with, by using phi, you are disguising this simple structure of the map. Now, once you construct this F, then you compose with L1 and L2. These are invertible affine transformations. Once you do this, then you have the public key for the MPKC. All right. So the end result, the public key is K and these n polynomial maps. That these are actually quadratic polynomials it comes from the structure of finite field. So it's not non-trivial. It's not trivial, but it's sort of basic algebra. So an attack scheme depends. Attack scheme is devised by using these quadratic polynomials. So an LE, this stands for linearization equation. So linearization equation for these public key is a quadratic equation, Q of xy. So it's you see that it's quadratic. This is quadratic and these are linear. It's qxy such that if once you substitute these fi bars for y, then it becomes 0. So now, then you immediately see that you can guess what the text is by plugging in the ciphertext. So you place ciphertext in yj, then this equation becomes a linear equation in x. So you solve enough number of linear equations and hope that you determine what the text is. So that's the essence of the linearization equation attack. So it depends on how many linearization equations you can find for a given ciphertext. So find enough LEs for f bar, then solving the linear systems may lead to the text. That's what I said. So the key problem is the estimation of the dimension of the space of the linearization equations. Yeah. It's quadratic, but it's non-trivial. So you start with x, sending x to the q to the theta plus 1, but any map of that form is, so once you write it in terms of the small field k, it becomes quadratic. So you see that x to the q is x. So if you use it repeatedly, then you get the linear equations, the quadratic equations. Any other? All right, now I'm going to explain one of the most basic um, topics in algebraic geometry. You learn this in the first couple of weeks of your introductory algebraic geometry course. So this is Segre embedding and global sections of divisors. So a prime divisor X, it's just an irreducible codimension 1 subvariety of X. So X is an algebraic variety. Then a prime divisor means it basically is f equals 0, a subvariety defined by a single equation. And it has to be irreducible, and it's a prime divisor. And div X is a divisor group of divisors. So it's generated by it's the free group generated by the it's not really free group. It's the group generated by the prime divisors modulo some equivalence. The equivalence I don't have time to explain it here. And X has to satisfy some mild singularity conditions. And these divisor groups are extremely important in algebraic geometry. So when you don't understand certain space, then you study the functions on the space. So these divisors really play the role of functions on the space. You understand the divisor group, then you understand the algebraic variety. So for instance, in the the fourth week of algebraic geometry course, you prove that the automorphism group of the projective space is PGLN. That's by computing. You prove that by computing by using the global section space of the hyperplane divisor. So, and the whole birational geometry and lots of algebraic geometry really centers around this divisor group, the study of the divisor group. And the Segre embedding is just that map. This showed up in Professor Gesinghyuk's talk, right? So it's a map from Pn cross Pm, product of two projective spaces, into another big projective space. So sorry. So you have Pn, so homogeneous coordinate. You have got n plus 1 homogeneous coordinates. Got n plus 1 homogeneous coordinates, then you just multiply them together. So you've got n plus 1 times n plus 1 homogeneous coordinates. So you map x, y to x times y. Then this defines an embedding. So this realizes a product of projective variety as a projective variety. Right, so you immediately see how basic this Segre embedding is. So when you're learning about a new category, you want to have a product structure, product in the category. And this Segre embedding gives you the product in the category of projective varieties. Okay, so why am I talking about this Segre embedding? Well, the key idea from my point of view is that if you do everything in the projective setting, then lots of things become clearer. So you have the public key f bar. So you've got this f1 bar, fn bar, and I'm going to introduce new variable x0. So I'm going to replace x sub I, little xi by xi divided by x0. This is what we usually do when we homogenize an equation. So you send 1 and x1 over x0 dot 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 to 1 f1 bar and fn bar. Then this is equivalent to, so it's a homogeneous coordinates in projective settings. So you can safely multiply every factor by the same number or symbol. So I'm going to multiply here this guy by x0. Then you get x0 through xn, and Now here I multiply by x0 squared because all these fi bars are quadratic equations. Therefore, you're going to have xi over x0 squared. So in the denominator, you're going to get x0 squared. I don't want that. I want to clear that out. So therefore, I'm going to multiply x0 squared. Then once you do that, then these these rational polynomials are going to be actually polynomials. So I'm just clearing out the denominator. So each x0 squared fi bar is a homogeneous quadratic form. It's very mild. It's homogeneous quadratic form. So this was the LE, linearization equation, for the public key. Then what I do is I homogenize this linearization equation. So I introduce variable y0 and I introduce variable x0. And the last term is d times x0 times y0. So this is a homogeneous of by degree 1, 1. Right? Then watch this. So if you go back to the Segre embedding, this was the Segre embedding. Now let Zij, so here I've got 0, 0 through n. So I've got n squared plus 1 homogeneous coordinates. So I'm going to name them Zij. Then in terms of these Zij, the linearization equation simply becomes a hyperplane. Aij, Zij plus dot 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 equals 0. It becomes a hyperplane divisor. All right, so I put this symbol. So this is the space of global sections of this divisor. So it's not very important. So what we do is, using this public key f bar, I'm going to build the map Pn to Pn cross Pn by 1 times f bar. So send x to x and f bar of x. And then you get a map from Pn to Pn cross Pn. Then what's the LE? So here's here's a problem for algebraic geometers. So LE is a hyperplane. Cij zeta is equals 0. It's a hyperplane on this. I'm missing this big projective space. Remember, the Segre embedding maps. Segre embedding maps Pn cross Pn to another big projective space. So this is a hyperplane on this divisor on this big projective space, and linearization equation is simply a hyperplane plane containing the image of this Pn. So you have a map from Pn to Pn cross Pn to Segre embedding. And the problem about the estimation of the dimension of linearization equations becomes so I didn't state it here. In algebraic geometry, the problem becomes estimate the dimension of the space of divisors, hyperplane divisors containing this guy. So a similar problems, but this is a little different from what we usually study. So we usually study the space of divisors that vanish on another divisor. So that's what we usually study. But anyway, similar problems are considered in algebraic geometry all the time. So once you once you homogenize everything and move to projective setting, then we can set this up for algebraic geometers to think about. So set up this way, then you can use hopefully you can use algebraic geometry tools to study MPKC systems from a different point of view. So I don't claim that I have a concrete result, but I do feel and I really believe that by by using this strategy, you can take a step or two further. So next is the classification problem. So let me read this if I have time. So this means that given a specific f, we can build a large family of NP cases by choosing different L1 and L2. So you define equivalence relation among all these maps. And what we do is you classify all these equivalence classes and then ask which are the good ones for the construction of NP cases. So this is straight from chapter 8, future research in MPK crypto systems by Professor Ding, Gower, and Schmitz. Are there any further work in this direction? Okay. So, well then, all right. I didn't do an extensive literature search, so I hope that what I'm going to say is somewhat new. But otherwise, we'll just take it as a survey talk. So of course, over a finite field, the space of equivalent classes of quadratic forms is discrete because there are only only finitely many polynomials. But approaching the classification problem in the discrete setting from combinatorial point of view it's not really the optimal way, I think. So one should consider this problem over an algebraic closure. So you move up to the infinite field and equip the set of equivalence classes with more structures and study its properties. So you can try to build a space of these equivalent classes and try to find some invariants or some sort of functions on the space to determine what are the good ones for the MPKC. This is from me at the 2016 PQC forum. Sorry. So anyway, so everything still depends on the homogenization. The only new idea is homogenization. You homogenize the map. So this was originally from affine space to affine space. Now I've got this map from Pn to Pn. So if I bar homogeneous forms, it doesn't have to be really quadratic anymore. It's a quadratic case. It's the classification is quite simple. Then composing with affine transformation is really nothing. It's just linear change of coordinates. So it looks like this. You have got map from Pn to Pn, and GIs are simple linear coordinates. You're multiplying this coordinate vector by a matrix. So G on G are elements of this projective general linear group. So in this setup, lots of things, only basic lemmas, tough lemmas are still tough, but lots of things become total triviality if you look at it this way. So I do believe that this is a much more natural setup to think about the MPKC, at least the Matsumoto Imai system. So this is meaningless to a lot of people, but a quadratic form is a member of certain vector space that algebraic geometers love. And this group G is the projective general linear group. G cross G acts on this space by you first act on X, and then I put this inverse so that it becomes a group action. Then the classification problem may be approached via studying this quotient space. So you have the space of quadratic forms, and you're quotienting out by this group action. All right. But in algebraic geometry, in topology, you just take the set of orbits, and you put a quotient topology, and that's it. But in algebraic geometry, that you get a non-Hausdorff space, so you have to be a lot more careful when you are constructing quotients. So GIT was devised by David Mumford in the 60s and 70s to treat this problem. So he was awarded a Fields Medal for his work on GIT. So its a basic definition is a member in this thing is semi-stable if there is an invariant form that does not vanish on that point. So there is certain notion that distinguish one point from the other. So one of them is good, semi-stable is good, and non-semi-stable is bad. Then I think I repeated that line. So the quotient space, this can be constructed by using this method GIT. I don't have time to explain this at all. But there is a quotient space that parameterizes semi-stable points. That's a typo. Thank you. That's the degree of the form that you are interested in. So in this case, it would be 2. So in fact, the conics are really too simple. So for over an algebraically closed field, there's only one conic. But here you have a series of sequences of conics, so the GIT is not totally trivial. And the good thing is that you're interested in the finite field situation, and when you want to do GIT, then you want to use geometry, then you have to you have to work over algebraically closed field. And the semi-stability notion behaves reasonably well on the field extension. So you can safely work over an algebraic closure. So the question for algebraic geometers. So lots of algebraic geometers. So I have my colleague Young Kim, who's a world's premier expert on invariants and moduli spaces. So can you find invariants or functions on this quotient space that tells you which forms are suitable for MPKC? So if you can find certain invariants, new invariants, or maybe old invariants. So if that invariant is good, then it's good for MPKC, otherwise it's bad. Right? And then there will be I think it will be very interesting for both cryptography community and algebraic geometry. So I'm just throwing out questions a lot without real results. All right, so I'm almost done. So next topic is direct attacks by Grosvenor basis. Yep.
So, can you introduce what is good and what is bad in a rough form? That is, if certain form contains some certain space, it's bad, or?
No, I'm really talking about good and bad in the most naive sense. So you want to find the fine balance between the efficiency and the security. Right? So that's all I'm saying. So an MPKC attacker needs to solve a system of polynomial equations. So Fi bar are the public key, and Yi's are they are the ciphertext. So if you can solve that multivariate equations, then you are successfully attacking the system. Now the corresponding algebraic variety. So I really have to subtract Yi from Fi, right? You're solving Fi bar minus Yi equals 0. You're solving those equations. So the corresponding algebraic variety is 0-dimensional because we are assuming that this is a cryptography system. So there is only one unique text for a given ciphertext. Although lots of in many cases this is not true, but not unique. It may not be unique, but I'm going to assume that it's zero dimensional. So when it's zero dimensional, then you can use Grosvenor basis. So with respect to what's called elimination order. So you compute Grosvenor basis with respect to elimination order, then you really get a simple equation, xi, so a single univariate equation. Then you solve the univariate equation by whatever method you can use, and then you substitute that value to the remaining equations, and you solve it one by one, step by step. Then you get the original text. So how much money does it cost to compute a Grosvenor basis? So there's what's called the Castellano-Mumford regularity. You can define it algebraically or more geometrically by using this cohomology. But the definition is not important. Right? There are certain things called regularity. It measures how the complexity of the equations and the relations between these equations, or polynomials. So with respect to the rev-lex order, reverse lexicography order, this regularity defined above is equal to the maximum degree of a Grosvenor basis. So this is the maximum degree is not the only measure that you need to consider, but it is the one of the most basic measure of complexity when you are computing Grosvenor basis, and it equals the regularity. And in characteristic 0, it is double exponential. So di is the maximum degree of the equations that you're working on. So and n is the number of variables. It's really bad. It's double exponential. It grows quite fast. And even worse is that this bound is sharp. So there's a really famous example by Mayer and Meyer, okay, right? The good thing is that there is only one example. All the rest, they in Grosvenor basis computation is quite fast. So, and I don't know the state of the art, but this is I read in Mumford's paper that this bound is probably true in positive characteristic. So in general, it's even worse. D to the 2 to the n factorial. So in practice, it works quite well. So by Faujaret, when the degree complexity is less than or equal to 5 for number of variables less than 160. So this is quite promising experimental results. So my idea, I want to really work over an algebraically closed field. So you switch to algebraic closure of your finite field. Then there is what's called the Hilbert scheme. So we like Hilbert scheme, algebraic geometers. It's an algebraic variety parametrizing ideals. So you're working with ideals, and there's a huge space that encodes all the ideals. And you have a what's called the regularity decomposition. So HM reg means the locus of ideals of M regularity, right? And the good thing is that the regularity decomposition, well, I did not state it, but oh yeah, I stated it here. 2 reg is open. So you pick one ideal randomly, then the chances are that that ideal defines a smooth algebraic variety, no singularity. Okay, then the ideal is 2 reg. So remember the regularity equals the degree complexity. So in this algebraically closed setting, so this 5 you can safely replace it by 2. But since the experiments were done in a finite field situation, so I think that's why it moved up to 5. So this tells you that in algebraically closed setting, if you pick the public key f bar randomly, then the degree complexity is 2. And I believe that this kind of regularity decomposition and it depends. It comes from the fact that the cohomology is an upper semi-continuous function, and these tools will give you a more realistic bounds, degree complexity bounds, on this Grosvenor basis computation. And that's it for me. Thank you.
Question?
So first I have to say this is very interesting talk. I think you have very interesting ideas, but actually this is a question I want to ask people in geometry for a long time already in terms of what you just said over there. So you think it's better to look at the problem from the perspective of algebraic closure instead of looking at the finite field itself. Is that correct?
Yes, but only because a lot of tools we developed works in the algebraically closed setting.
Yes, but
Yeah.
I actually disagree in this case. But my thought was, see, when we solve a system equation of a finite field, in particular over small characteristics, we automatically include the field equations. In that case,
Right.
yes. So in that case, the problem becomes much simpler. So let's look at the case that you do not include the field equations. For example, like Q equals 31. The reason we like it because you cannot include it because you cannot use it because we never can reach the degree 31. In this case, you are solving the equations over algebraic closure field. In this case, if from Bezout's theory, we know the number of solutions. For example, you have any equation quadratic case, you should have 2 to the n solutions already. And that means actually the closure equations are very difficult to solve. So it's kind of contradictory in the sense of what you're saying. You know what I mean?
Yes. So if you are actually solving equations, then you do want to work in your specific situations. So what I'm claiming here is that when you are trying to give a rough bounds or some sort of estimation of things, then it's better to work over algebraically closed field and algebraic closure. And
but from what I just said, is that seem to not match because originally I have only one solution, yeah, and then once you go to algebraic closure field, I should have 2 to the n solutions. Then 6. So I don't know how to say this. So
yeah, I should say that not everything. I don't claim that not everything will work in the finite field situation.
maybe I asked the wrong question. I mean, so one of the key questions we would like to understand is the complexity, how complex to solve the system equations. So from this approach, what kind of new things you can tell us in terms of the complexity analysis? Maybe you can say a few words on that.
What are the new things that I
Can tell us we don't know about the complexity, how to solve system equations.
Well, if I had it, then I would have said it.
Okay, thank you.
So, yeah.
Okay, thanks.
That's an unfair question.
Okay, thank you.
Okay, other question? Okay, it seems no question. Let's thank the speaker again. Thank you.